Hello. Good afternoon, dear student. My name is Kumar Bhukta. I am the assistant professor in the Department of Mechanical Engineering, HIT Haldia. Today I am going to teach about one of the most important topic, heat exchanger, which comes under the subject heat and mass transfer. This subject basically deals with, as you know, the transfer of heat between the system and surroundings, and with different systems, open system, closed system, like that. Already we have talked about several types of basic uh, the heat devices in the previous classes. Today I am going to talk about the another which is very useful, especially used in the industry and any other process plant. The name is heat exchanger. As you know, the definition of heat exchangers, it is a steady flow device where the heat gets exchanged between two fluids. The two fluids here, the hot fluid and cold fluid, without taking any heat from the ambient. Means this device only just exchange the heat between the two fluids. One is hot and another is cold fluid. So also one thing you should remember, it never be take any heat or any energy in the form of heat from the ambient, and also and do not lose any heat from the system, that is heat exchanger. So as you know, I am just going to draw the typical representation of heat exchangers. Suppose this is a simple, a typical diagram, very simple schematic diagram. This one, this is the heat exchanger. Here it is the hot fluid. Hot fluid in. Here, this is the arrow symbol, and this one is the hot fluid out. Out. And this one, this is the cold fluid. Cold fluid, which takes the entry, that is in. And this is the cold out. Cold out. Now what's happened? This is, as I already discussed or told, this is the steady flow device. Steady flow device, so there will be no mass accumulations within this system. If this is the control volume, I am as per the system constant, the volume remains constant, and within this there will be no mass accumulations within this device. Means that is the steady flow device, as you know. Now what happens? There is two fluids. One is hot fluids, and so they now get heat exchanged from hot fluid to cold fluid. So this is the Q amount of heat, dQ amount of heat. D I am taking because this is we have taken the elemental sections. Small amount of heat gets transferred from hot fluid to cold fluid. Now what will happen? So during this change or transfer process, the hot fluid become cold and cold fluid become hot. So this is the basic representations or schematic of the heat exchangers. Now we will talk about the uses where we can find the uses of heat exchangers. Especially there are a lot of applications, especially in the industry, starting from the steam power plant, gas power plant also, and any chemical process plant. RAC, I have talked about in the last class. RAC, refrigerations and the air conditioning system. So there are lot of applications of heat exchangers are there. As you know, the condenser itself, condensers, and the in the condenser of uh, in the refrigeration systems, you know, it is one of the easiest example of or most common example of heat exchangers. In the car, you have seen there one radiator, which is the another example of heat exchangers. Now I am going to the talk to the next topic. Example. There are some examples of heat exchangers I have written here. So first one is the surface steam condensers. So this is it comes under the cell and tube type. What is that cell and tube? As the name suggests, so this is there will be cell there like that. Means closed vessel. Okay. So obviously there will be two opening here. So I have written here two opening here. Okay. So heat would be just gets transferred. So opening means here means in hot fluid in out hot. So there will be a pipe. There may be a lot more pipe. I am just schematically presenting one with one pipe. So inside the pipe there will be obviously flowing of what? Flowing of cold fluid. Okay, cold fluid in and out. Here inside, outside. Cold. So detergent is cold. Okay. So now while the hot fluid is passing, so obviously it would be just transferred from hot fluid to the cold fluid inside. Okay, and they are not actually not mixing them. They are separated by pipes inside. Okay, and as the name, so tube here means the pipe and cell means it's a closed container like that. Okay, so this is the cold type of this is the surface steam condenser type of heat exchangers. Next, very common and very one of the most important uh, devices, which is known as the heat exchangers, specially used in the steam power plant, where it is you will find the use in the boiler sections. So all starting from 2 to 5. So these are the most important components of heat exchangers or heat exchangers. One of the heat exchanger example of heat exchangers, specially used in the steam power plant. Econometer, you know, it is used in the boiler sections where the rejected gas, flue gas, which is known as the hot flue gas, which is again utilized so that we can minimize the wastage of heat while do not expose to the atmosphere, direct atmosphere. So what will happen, that hot flue gas is utilized for heating up the feed water. So feed water is generally having temperature less than that of the hot flue gas. It is cold. So that would be utilized so that in the next processes we can use that feed water. Okay. Superheater is also one of the most important example of heat exchangers where the hot flue gas again be utilized to make the steam to reach in the condition or state dry saturated. Okay. Next, air preheater, again it is used in the furnace where we can that heated combustion air is utilized to heat the gases. Okay, so hot flue gas is utilized, that heat is utilized to use or heat up the air itself. Okay, so air repeater again is one of the example of heat exchanger. And cooling tower, you know, here actually the two fluids are gets mixes in the cooling tower. Okay, and the just the warm water which is coming back from different power pack which is used in the industry hydraulic systems that heated or warm water that would be released there by passing the air. Okay, so cooling tower we will talk about more in the other classes. So you just remember these are the most common example of heat exchangers. Next, different types of heat exchangers. So in abbreviations, the heat exchanger we have written here HE. Okay, first one is the direct transfer type heat exchanger, which is also known as the recuperator. And second one is the storage type, which is known as the regenerator. And third one, the direct contact type. So first one I will talking about now, the direct transfer type heat exchangers, which is also known as the recuperator. So what is that? Here the two fluids do not mix up with each other. Two fluids here only here we will be discussing. One is hot fluid, another is the cold fluid. So they never be mixed each other. Okay, so they will be separated by means of some pipes. Okay, and the pipe is made up with some metallic material, metal. Okay, obviously metal is good conductor of heat transfer. So heat would be passing through that metallic conductor and ultimatum the hot fluid and cold fluid, they would each other exchange the heat. Now the direct contact type heat exchangers we have discussed. Then storage type, storage type is one another type of heat exchanger which is known as the regenerator. Here we at a time we do not pass or allow the two fluids at a time. So after a certain interval, first we will just allow to pass the hot one, and that would be passes through a heat matrix. I am just presenting here. It is like that. So this one is the heat matrix. This one is known as the heat matrix, which is there inside that closed container like that. Matrix, heat matrix. Okay, heat matrix. Now here suppose hot in. So here hot out. So we are just giving the arrow sign here. So giving arrow sign here, hot out. Okay. And here cold fluid is getting cold, cold in, and cold fluid again getting out, cold out. Now what will happen? At a time we do not allow the two fluids to pass through this heat exchanger. Now in the first interval of time we will allow to pass the hot fluid inside this one, inside this entry, this inlet pipe. Now what will happen? That fluid will be just passing over this heat matrix. Now this heat matrix is the ability to store heat. Okay. So what will happen? So as we know, heat never be energy. Energy never be lost. So that heat which is present in the hot fluid, that would be stored inside this heat matrix. Okay. So after a certain time elapsed, means suppose 15 or 20 minutes during this pass, we just stop to pass that hot fluid. Now what will happen in the next sessions or next interval of time? Again, we will allow to pass the cold fluid. So during this, what will happen? Whatever energy, heat energy stored within this matrix, that one is again released that heat, that released to the cold fluid. So whatever stored, that heat energy now means transfer in the cold fluid. And cold fluid is passing in this way and take exit in the exit port of that heat exchangers. And what will happen as the heat again transferred to the cold fluid, so cold fluid become a little bit hot. So in this way, so the heat would be gets transferred. So this type of is known as the storage type of heat exchanger, or also known as the regeneration or regenerative heat transfer. So next we will go for the direct contact type. This is one type of heat exchanger where the two fluids are mix each other, and finally we will get an ambient amount or ambient temperature level of temperature where we can get the hotness or coldness of fluid as per our requirement, which is the one of the most example of direct contact type of heat exchanger is the cooling tower. Okay, cooling tower we already have discussed a little bit. Just give the idea. Again, the heat exchanger may be classified as per the transfer type. Okay, as per the directions of fluid, in which direction they get take entry and leaving out from the heat exchanger. So based on that, that is called the flow arrangement. So as per the flow arrangement, we can again segregate or classify the heat exchangers like that: parallel flow heat exchanger, counter flow heat exchanger, and cross flow heat exchangers. So as the name suggests, first one, the parallel flow heat exchangers means here, if we draw the temperature curve, so along y-axis this is temperature, along x-axis it is area A, or maybe length of the heat exchanger. Okay, so maybe length of the heat exchangers. So here what will happen? This is hot fluid and this is the cold fluid. So the directions of flow of the two fluids is along same directions, means they are parallel to each other. So this is TH1. Okay, TH1, and this is TH2, and this is TC1 and TC2. So this is hot fluid inlet 1 and inlet temperature TH1, and this is outlet temperature hot fluid TH2. Here cold fluid entry temperature means TC1 and outlet temperature is TC2. So look here. So this is the arrow symbol we have denoting here because they are parallelly flowing, means the directions is along the same directions. So this is the first parallel flow heat exchanger. Next we'll go for the counter flow. Same thing. The counter flow, just the direction of flow of the two fluids should be different, means in opposite directions, not different, in opposite direction. Suppose this is the hot fluid, hot, so and the cold fluid, so cold fluid like that. Okay, so here the temperature TH1, here TH2. Okay, and here the temperature TC1, that is cold fluid inlet temperature, and here cold fluid TC2. Okay, outlet temperature. So look here, the arrows is just opposite to each other. Okay, so this is parallel counter flow heat exchanger, not parallel, counter flow heat exchanger. And next one is the cross flow heat exchanger. In cross flow, as the name suggests, they are crossing to each other, means they are orthogonal to each other. So I am just the flow arrangement would be just like that. So if this is the heat exchanger, so So this one are this parallel vertical lines are the hot fluid in, here hot out, hot out. Okay, and cold fluid would be just perpendicular to each other, means they are crossing each other. Okay, so these are orthogonal to each other. So cold in, cold out, cold out. So if I put the arrow, it would be like it. So they are crossing to each other. So this is cross flow heat exchanger. So the temperature profile hot fluid would be like that. So hot fluid would be cooling. So the temperature gradient would be just like that. And here the cold fluid become hot, means the temperature profile would be like that. Okay, so these are the temperature profile, and these are the temperature profile of the hot fluid. So this is the temperature profile of the cold fluids. They become hot, so temperature gets increased, and here the hot fluid loses its temperature, means the curve gradually goes downward. So this is the cold fluid, hot fluid temperature profile. So this is as a whole the cross flow heat exchanger. So now we will go for in details the parallel flow heat exchangers. In details means we will determine here the rate of heat transfer in the parallel flow heat exchangers. So now is a schematic diagram I am representing here. So this is okay. Yeah. This is not correct actually. Means we have to make two ports. Okay. So in the previous one we have drawn four ports. Actually it would be two ports. So in the middle there will be another pipe just like this. So this is the heat exchangers. Here this is cold fluid. Cold in. Here cold out. Okay, and here hot in. Hot in. Here hot out. Hot out. Here hot out. Now what will happen? So it is parallel flow. So this one the entry, this is the leaving out of that hot fluid, and this is along this directions the cold fluid takes entry, and this is leaving out. Okay, from the heat exchanger. So the flow arrangement is in the same directions, and this is well insulated, so that there would be no energy interactions between the system and the surroundings. Okay, well insulated. So these are the insulations I have provided in this. Now, so this is parallel flow. Now what we have to do? We have to determine the rate of heat transfer. Calculate. We have calculated the rate of heat transfer uh, in the parallel flow heat exchanger. Now look here. I am just now draw the temperature profile of parallel flow heat exchanger. So the temperature profile would be like this. So this is TH1, the inlet temperature of the hot fluid in, TH2, the outlet temperature of the hot fluid out. This one TC1 and this one TC2, cold fluid in, cold fluid out. Okay, so this one del T I. Here I means is the inlet sections of the heat exchanger, and their difference of temperature is known as the del T I. And this one, this difference is del T E. E for here, E, or you can write here O, outlet, or maybe exit, TE, del TE. Okay, so this is the temperature profile. Here, this is temperature along Y direction, and this is the length. Okay, length, or sometime X, or area. Okay, A0. A0 is the, A0 means 0 is what? This is the outer or outside area of the, in the inside tube or pipe. So that is A0. Okay. Now we have taken, for our analysis, we have taken an elemental sections. So elemental sections here we have taken for our easiness of calculations, or we have now our focus idea within this elemental sections. So the length of the elemental section is dx here. The length of the elemental section is dx here. Now here you know this is another heat difference. Okay, so here TH. Okay, if the average temperature within this element system is TH, and here also there is a little bit difference in temperature. So this one is the average temperature within this element section is the TC. Okay, and their difference is denoted as del T. Okay, del T. Now this is the temperature profile of the parallel flow heat exchanger. Okay. Now from this we could write, we will just focusing within this elemental sections we have here. So from here we can write del T is nothing but what? Del T is nothing but the temperature of hot fluid minus temperature of cold fluid. Okay. Now it is the elemental sections we are doing the analysis. So the change of the temperature D, del T, it would be nothing but what? DTH minus DTC. Just you put a D. Okay, DTH minus DTC. Okay. Now there would be a heat transfer. So from hot fluid to the cold fluid. So this is dQ. Okay. So this is dQ. Now that dQ would be calculated in this formula. Okay. So dQ would be what? It would be mH. mH, you know here, mH is the mass flow rate. Mass flow rate. You know mass flow rate deals with the continuity equations. It is as it is steady flow device, so it would be constant. Okay. So this is the mass flow rate of hot fluid, and this one is the mass flow rate of the cold fluid, MC. Okay. So this would be CH. Now the specific heat of the hot fluid is this one. Unit, you know, unit you just concern with always with unit. Okay, kilojoule per kg Kelvin. This specific heat. Okay, and that temperature difference is DTH. We have put a minus sign here because the hot fluid gets cold. Again, it is equal to MC dot CC. CC is again, you know, CC is the cold fluid, the specific heat. Okay, DTC. Okay, and again it is related to the equation heat transfer between the two fluids. Okay, you know this is as per the heat transfer equation. This one U0 A0. U0 A0 and del T. That temperature difference del T, you know. Now A0 is the area, okay. That dA0 means the area, outside area of that elemental sections, outside area of that pipe, okay. So it is nothing but pi dO into dx, okay, that length dx. So this is the equations we can, energy balance equations we can write here, okay. Now from here we could write, so dth, okay, so dth, it would be nothing but dq by minus mhch, okay, and from here dtc, it would be what, dq by what, it would be dq by mccc, okay, mccc. Now we will put these two term getting from these equations over here, okay, over here. So just putting, so putting these two terms, we will be getting what, d del t is nothing but minus this value which you know, dq minus dq mh ch, again minus dq what, dq mc, the mass flow rate, and cc, okay. So minus dq is common, taking common, so it would be 1 by mh ch plus 1 by mc dot cc, okay. So this, within this parenthesis, this is written a constant mu p. Mu p is a constant term which is nothing but within this parenthesis, this one, okay. So here p for represents the parallel flow, okay. Now in the next line, what we will be writing, okay. Now this is the equation, final equation. Now we will integrate that equation. So integrate over two limit. So del t I or I, okay. So del t e for exit here, okay. D del t, it would be what? It would be just integration of mu p is common, okay. Mu p is common dq, okay. So minus is there, okay. Minus is there, that minus sign. So it would be what? So del t, it would be del I minus, this is minus del t e. Actually, it would be del t e minus del t I. As it is minus sign, so we have written this one first. This is first. Del t I minus del t. It would be what? Mu p into q. Mu p into q. And from here, we will be writing mu p is what? Mu p. Mu p is that constant term. It is nothing but del t I minus del t e del t divided by q, okay. So up to this clear, q up to this clear. Now again we could write from that equation, so these equations, this term is nothing but what, d Q. Okay, this term is again nothing but dq. Okay, so now we can erase that one. Again, we have just got dq is what? Dq is nothing but u0 dA0 del t. Again, del dt. Okay, del t is, what is this? Mu p by dq. Okay, mu p by dq. We have written this. Okay, we have written this. Now, what will happen? That dq from here we could write dq is what? From here dq is what? It is d del t by mu. Put that value over here. Okay. So instead of dq, you could write this one. D del t mu p. Actually, it is mu p. Okay. It is mu p. Parallel. Mu p nothing but u0 dA0 del t. Okay. Clear? Up to this clear? So now again rewrite this del t, that coming here, that del t coming here, it is nothing but u0. This u0 you know overall heat transfer coefficient. Okay, so dA0 mu p, dA0 mu p. Again we have to integrate this term. Again you have to integrate this term. So integrate this like that. Okay, so integrating. So this is the change of temperature. So integrate like this. Okay, so between two limits I and E. Here I for inlet and exit. Okay, so next what will happen? Next what we can get? Just erasing this one. So here, so this is the equation. Okay, so here there will be, this is the derivation integration of this. It will coming ln. Ln means you know log base e. Okay, log base e. So it will be del it would be del t I minus del t e. Okay, and here it would be mu p constant term u0 a0. Okay, mu0 a0. Now from here the value of mu p now would be, we will putting that value there. Okay, mu p. So again erasing the upper one. So putting that mu p value, so ultimately what we are getting? Del ti minus del te. It would be putting that value there. So it is del ti minus del te divided by q. Okay, divided by q, and here u0 a0. Okay, u0 a0. So from here we will be getting q. That q is our actually targeting parameter. That is the rate of heat transfer between the two fluids, that is hot and cold. That q, rate of heat transfer. Okay, in the rate from q dot. Okay, so it would be what? del Ti minus del Te divided by ln del Ti I divided by del Te. Okay, here U0 A0. Okay, now this term, I'm just boxing this term. This term is known as the what? This boxing term is now known as or Q is what? Q is U0 A0. Okay, so del T LMTD. Okay, LMTD. Here LMTD is what? Log mean temperature difference. Okay, log mean temperature difference. So it is nothing but this term within this box, this term. Okay, so this is the equations. This is the heat transfer equation, rate of heat transfer equations of the parallel heat transfer. And this is also equal to what? This is also equal to MHCH. Okay, the temperature difference between the two plates. In the previous picture, we have just denoting TH1 minus TH2. Okay, again for hot fluid, again exchange between the hot and cold, so the energy remains same, so it may be changed. So from for the cold fluid it would be what we are writing in the here C TC2 minus TC1. Now the question comes, why we don't write here TC1 first? We have written here TC2 first, because cold fluid become hot. Hot means its temperature is more than TC1. That's why the difference is written TC2 minus TC1. So you can calculate that rate of heat transfer by any one of these out of these three equations as per the data given in the problem. Okay, so many problems comes from this parallel fluid exchangers, and it is mostly used such type of in different industries where the parallel flow mainly we can focus. Okay, so Q, this one is again equal to this one and this one. So as per your data given, okay, you can calculate that. Or today after this, so in the next class we will go for the same analysis for the counter flow heat exchangers. Okay, so okay, thank you for joining today's class. Okay.